For this module in dynamics, we'll be learning about curvilinear motion. So the learning outcomes after this module would be to explain the concepts of position, displacement, velocity, and acceleration in relation to curvilinear motion, and explain and apply the concept of projectile motion. Now, what is curvilinear motion? Now, curvilinear motion occurs when a particle moves along a curved path. Okay, so since this path is often described in three dimensions, vector analysis will be used to formulate the particle's position, velocity, and acceleration. So that means we will be using vectors in this module. So the general aspects of curvilinear motion are discussed, and in subsequent sections we will consider the rectangular coordinate system often used to analyze this motion. So an example of curvilinear motion would be this motion right here. Alright, so that is a ball moving along this path which is curved. Okay, hence the name curvilinear motion. So it has a position on the x-axis and the y-axis if you're using a rectangular coordinate system. All right, so the next entries here on your module are pretty self-explanatory. I think you can read this on your own. In a nutshell, position, it just means that the position of a particle is measured from a fixed point O. Okay, so this is the radius. Basically, it's a radius vector, or we can call it. We will be calling it the position vector. Okay. Next, displacement. Again, that's just the change in position. Velocity. That's a change in position over the change in time. Instantaneous velocity, the same thing with module 1. Also, velocity is always tangent. The velocity vector is always tangent to the path. Next is acceleration, is change in velocity over change in time, and we will be introducing the concept of a hodograph. A hodograph is basically a curve wherein your vectors are the tails of subsequent velocity vectors are plotted at a fixed point O prime, and their arrowheads touch points on a curve. Okay, so this is called a hodograph. Okay, so basically this is just a graph that describes the change in velocity, because there is a need to describe that change in velocity. And also, next is by definition, the derivative A acts tangent to the hodograph, and in general, it is not tangent to the path of motion. So acceleration is not tangent to the path of motion like the velocity vector. Okay, here there is a clarification as to why, but the most important entry here is that in order for the particle to follow any curved path, the directional change rather always swings the velocity vector toward the inside or concave side of the path. So that would mean the acceleration vector is it's either towards the center or towards some point on the path. All right. So moving on to curvilinear motion, this is basically just moving on to rectangular components rather. So we will be focusing on, in this section, we will be focusing on curvilinear motion with respect to the rectangular coordinate axis. All right. So since there is such a thing as 3D motion, right? There is a need to express position in terms of x, y, and z coordinates, right? And that is why this equation M2-3a is existent here. This is basically the position vector with respect to I hat, j hat, and k hat. Okay, we already went over this in vectors, so just refresh yourselves. You already know how to get the magnitude of that and the unit vector as well. The velocity, you can skim over this. The point is that if you have an x, y, and z component for your position, you surely have an x, y, and z component for your velocity as well. Furthermore, it's the same thing. It's still the first time derivative of r, okay, or the position vector, and the acceleration is also the second. Is still the second time derivative of your position vector, or the first time derivative of your velocity vector. All right, so you have x, y, and z components right there. So important points for this section are curvilinear motion can cause changes in both the magnitude and direction of the position, velocity, and acceleration vectors. Velocity vector is always directed tangent to a path. Acceleration vector tangent to the hodograph but not tangent to the path. If the motion is described using rectangular coordinates, then the components along each of the axes do not change direction, only their magnitude and sense or algebraic sign will change. And by considering the component motions, the change in magnitude and direction of the particles' position and velocity are automatically taken into account. So this is basically pretty straightforward stuff. Also, the procedure for analysis would be establish a coordinate system, and when dealing with kinematic quantities, the motion equations that we derived in the previous module can still be used. Considering that you take into consideration that there are such things as constant acceleration or constant velocity. Okay, so you still have to be very careful about these things. So to solidify our understanding, we will be solving an example.